Okay, so now everything we learned in 3.1, that's all background, calculator, where buttons are, E, all that stuff. Now we're going to use it. So in chapter 3, section 2, we're going to talk about the derivatives of exponential and logarithmic functions. Basically, there's some special cases. I'm going to point them out to you. The slide goes over how they come about, how to find derivatives. You're not responsible for that, but you are responsible for what to do the derivative, how to take the derivative. Okay? And I'll explain to you what I mean. So if I want to find the derivative of e to the x, this is the background. You're not responsible for the background. Just look at it, be aware of it, how it comes about. No. Yeah, you'll see it's going to get a little crazy flashing. So if you take the limit as h approaches 0, e to the h minus 1 over h equals 1, and we go, remember the long way of doing derivatives? If I take the long way of doing derivatives, f of x plus h minus f of x all over h, clean it up, work it all out as the limit of h approaches 0. Can you appreciate all this hard work that went behind the shortcut I'm about to teach you? We find that the derivative of e to the x, after all this work, do you know what the derivative of e to the x is? E to the x. So what's the derivative of e to the x? E to the x. Why? Do we like, what's the derivative of e to the x? E to the x. Okay? So number 1. Special cases, let's on the side somewhere, let's have a little piece of paper, and let's log all these. So these I'm going to call special cases. Derivatives. Number 1. I'm going to keep a little list. Special case derivatives, and they're special because it's like e to the x. So what is if I had e to the x, what's the derivative of e to the x? Number 1. Not too bad? Are we liking this section so far? The derivative of e to the x is e to the x. And we're going to keep a list on the side of all the ones I want to point out. And then we're going to use them, just like everything else. Good? So the derivative of e to the x is e to the x. Be careful when using the calculator that use the E button and not the power rule. E is special. Okay? What about logarithmic function? So if I want to take the derivative of the log, notice that the derivative of a log, well, the picture of a log, is the inverse of y equals b to the x. They have that reflection over it. Again, just background. Log of x equals log 10, base 10 of x, and ln of x is the log base e of x. Just some background. And if we do ln of x, what's the derivative of ln of x? Now again, anytime I ask, how does it come about? You will know the shortcut, but how do we get derivatives? We do it the long way. If I want to take the derivative of ln of x, we have to do f of x plus h. Then we subtract f of x. We divide it by h. We work it out. Algebra. See how this can get really long? It's all algebra. The limit as h approaches 0. Algebra. Take the limit as h approaches 0. We get the ln of e. What's the ln of e? They cancel each other out. All that work. What is the derivative of ln of x? 1 over x. Okay? So, special case number 2. If you have ln of x, what's the derivative of ln of x? Okay? I'm showing you the y and where it comes from. But what you need to know is where do they all come from? Doing the derivative by definition. F of x plus h minus f of x over h as limit as h approaches 0. H approaches 0. Okay? So there's 2. You have an appreciation of doing it the long way. So, using those 2, we can start solving some derivatives. Okay? So, I'm going to write it a little differently. Well, I'll write it a little differently. Okay? Let's do this one together. If I ask you to find the derivative, let's go nice and slowly. Okay? First of all, when there's a number in front, we leave the number in front. Okay? We did that for derivatives before. Then, here's the new stuff. What's derivative of e to the x? Ta-da! Not too bad. Now we take the derivative of the second one. What happens to the number in front? Stays in front. What's the derivative of ln of x? So I would write our final answer as 3 e to the x plus 5 over x. Means the same. Any questions on this one? Okay. Let me get you another one. So basically, I can ask the other derivatives we've done before, and I can throw in these new derivatives, these new special cases. Okay? So here's the next one. Remember, let's always look at it first to make sure we're okay. So, can we, especially after our last chapter, can we take the derivative of x to the 4? What's the derivative of that? 4x to the 3rd. No problems, right? Let's look at this one. A little bit of a problem. ln of x to the 4. Why is it different? What's weird about it? It's x to the 4. Ugh. I don't know that one. I know what ln of x is. What's the derivative of ln of x? 1 over x. So what's my problem right now? That 4. So we're going to have to remember our log properties. So to do this one, we're going to have to rewrite first. Does the first one need to be rewritten? Nope, not at all. And then we have to go back and remember. When we learned log properties, that exponent can be moved. If we have an ln or a log, that exponent can be moved. Where would it go? It goes to the front. That's a log property that we learned before, that the exponent goes to the front. We even used it when we did algebra, right? So is everybody okay with the rewrite? And because I rewrote it, is the ln of x by itself now? Now take the derivative. So just like we did before when we have to rewrite it, this is an example where we have to rewrite first, now take the derivative. Remember my symbols, f of x is just the original, f prime of x, that's my derivative. So just like before, we may have to rewrite first. So take the derivative of that. Okay, so what's the derivative of x to the 4? 4x to the third. Minus, what happens to the number in front? Stays in front. What's the derivative of ln of x? So I would write the final answer as 4x to the third minus 4 over x. So far, we only know the derivative of e to the x is what? E to the x. Now, if it's e to the x squared or 2, that's something different. We only know e to the x right now. And we only know what's the derivative of ln of x. 1 over x. Again, not ln of x to the fourth, just ln of x. So keep those when they show up, we know how to deal with it. Okay? So those are the 2 examples we just covered. Now we're going to talk about logarithmic and having a base. So we're going to talk about the derivative of a log. We're going to talk about derivative of a base raised to the x. So how do we take the derivative of a log? Well, we know that log and base can be rewritten as each other. So for example, if I had y equals log base b of x, remember doing our rewrites? I can write in exponential form b raised to the y equals x. Remember doing that? So these two are the same. These two are the same. And that's how they're going to help you understand what the derivative is. Again, give you the background, and I'll show you the shortcut. So if I want to solve this, by equals x, I'm going to ln both sides. Why will I ln both sides? So the y will go to the front. The y will go to the front. Then if I want to get y by itself, how do you get rid of times ln of b? Divide by ln of b. Y equals 1 over the ln of b times ln of x. Therefore, the log b of x equals 1 over ln of b times ln of x. And if you take the derivative of that, you get 1 over ln of b times 1 over x. Now, let me show you what happened. 1 over ln of b is just a number. What do you do to a number in front? Stays in front. What do you do to a number in front? Stays in front. And what's the derivative of ln of x? 1 over x. Are we okay? So here's what you need to know. What you need to know is when, go back to our special case. If you had log, let's say log base 5 of x. Let's just pretend the base was 5. Okay? The derivative, because of what we just gone over, is 1 over the ln of whatever the base is. What's the base in this case? 5. And if it was 6, I put 6. If it was 7, I put 7. If it was 10, I put 10. Times 1 over x. Okay? So, what you need to understand is if I had log base 5 of x, what would the derivative be? 1 over the ln of 5, whatever the base is, times 1 over x. 1 over the ln of 5, which would just be a number, times 1 over x. Okay? You have this on the side. Anytime a log comes up, that's what the derivative will be. Anytime a log comes up, that's what the derivative will be. And why does that work? Why does that work? This explanation. Okay? We converted exponential form. We solved for y. We took the derivative of it, and you see where everything falls. Okay? Same idea, same idea. What if I had a number raised to a variable? Okay? If I had a number raised to a variable, any number raised to a variable, and I wanted to solve for, let's say, x. I ln both sides. Now the x can go to the front. And if you want to solve for x, or actually if you want to solve for y, I'm sorry. We E both sides. So the E and the ln go away. We have E raised to the x, ln to b. Again, don't worry, relax, relax. You can write it as e to the cx. The c goes to the front, c e to the cx. But here's what you need to know. Because of the explanation, if you took the derivative of a number raised to an x, it becomes, rewrite it, ln to the base. Rewrite it, ln to the base. Rewrite it, ln to the base. So, let's put that on our special cases. If I have f of x equals 2 raised to the x, and it's any number raised to the x, the derivative would be, step 1, rewrite it. Step 2, ln of the base. What's the base? 2. So, if this was f of x equals 3 raised to the x, I would write 3 raised to the x, ln of 3. If it was 4 raised to the x, 4 raised to the x, ln of 4. You see the pattern? And why does it work? The explanation on the previous slide. So, quick summary. The derivative of e to the x is e to the x. The derivative of a number raised to the x is rewrite it, ln to the base. Rewrite it, ln to the base. The derivative of ln of x is 1 over x. And the derivative of log base b of x is 1 over the ln of the base times 1 over x. Those are your 4 special cases. Those are the 4 special cases that when they show up, you'll know how to do it, and you've seen where they come from. They either come from the derivative definition or from rewriting them, then taking the derivative. So, now we're able to do some examples. So keep those 4 on the side, and I'm going to give you 2 examples to try. Take the derivative of log base 5 of x, which should be very easy because I gave you that as your example. And then 2 raised to the x minus 3 raised to the x. So give these 2 a try. All right, let's go one at a time. As soon as you have a question, let me know. Go nice and slow. So, we see a log. So we immediately go to our special case derivatives. We see what the pattern is, and we follow. So to take the derivative of log base 5 of x, what do we do? 1 over ln of times 1 over x. You can leave it like that. You could rewrite it as 1 over x ln of 5, which looks a little bit nicer, but both are correct. Both are correct. Any questions there? So what are we doing? When we notice a special case, e, log, ln, number raised to a variable, we look at our special sheet, we follow the pattern. Okay? Next one. I have 2 special cases. So I look at my sheet, when I have a number raised to a variable, rewrite it, ln to the base. So, rewrite it, ln to the base. So the derivative of 2 raised to the x is 2 raised to the x times ln of 2 minus, what's the derivative of 3 raised to the x? 3 raised to the x times ln of 3. Done, done, done. We okay? So again, you have an appreciation for where they come from, but if they show up, you know what to do. You have an appreciation for where they come from, but if they show up, you know what to do. Okay? Now we're just going to do 3 or 4 word problems, and we're done. Questions there? All right. So, word problem number 1. And we'll practice our calculator, we'll practice our derivative, and all that stuff now. An online store sells guitar strings. If the store sells X set of guitar strings at a price of P per set, then the price demand equation is P equals 12.5 times 0.998 raised to the X. Find the rate of change with respect to demand when the demand is 100 set of guitar strings. Interpret the results. Okay? So step 1, let's write it down. P equals 12.5.998 raised to the x. So that's our equation. That's our equation. And what I'd like you to do, and we'll do this together, we'll talk it through. We're going to take the derivative of that. Okay? Now, don't write anything down. Don't write anything down. But work that out in your head. Work that out in your head. What you would do. Don't write it down. I know that looks weird, but it's just like the ones we've done. Okay? Step 1. There's a number in front. What do we do when there's a number in front? Keep it there. Question so far. Is this a special case? Which one? Is it an E? Is it an ln? Is it a log? Is it a number raised to a variable? Number raised to an x. So what's the pattern? Rewrite it, ln of the base. So step 1, what do? Rewrite it. Times what? ln of the base. Now, we could multiply the 12.5 times the ln of 0.988. Well, let's just leave it the way it is. Now, just to remind you, P is what? P is price. X is it's number of sets. We're talking about guitar strings. Okay, so our P stands for price. X is number of guitar string sets. I'm going to test you on your calculator now. I want you to go to the calculator. Y1 is the original function. Y2 is the derivative function. Y3 is the derivative in the calculator. And then you're going to plug in 100. I want to know what P of 100 is. I want to know what P prime of 100 is. And then we'll have to write down what it all means. So let's practice the calculator. Y1 is the original function. y2 is the derivative function. y3 is the derivative in the calculator, so you can check if it's right. Practice, practice, practice. So all we're doing is taking all the stuff we've learned and adding special cases. E, ln, log, and base raised to the x. So let's go to the calculator. Clear out y1, clear out y2. y1, 12.5, 0.998 raised to the x. So the original in y1. The derivative, 12.5, 0.998 raised to the x times ln of 0.998. So y1 is the original, y2 is the derivative. How do I do the derivative in the calculator again? Math 8, this version is x, bars, y bars, function y1, x. All stuff we've gone over, right? Nothing new, it's just we're doing special cases now. Go to the table feature. Get rid of any old ones, type in 100. What does 100 stand for again? Guitar string sets. What is y1 going to tell me? The price. So y1 tells me at 100 guitar string sets, the price is $10.23. At 100 guitar string sets, the price is $10.23. Now, how do I check if my derivative is correct? Which one should match? Y2 and Y3. Do they match? Yep. Question. Would you put a what? Oh, sure. So Y2 is this one. Y2 is this one. So in Y2, it's 12.098 raised to the x, ln of 0.998. So y2 is the derivative function. Y2 is the derivative function. Be careful, careful, careful. And that's what's nice about checking in the calculator. So the derivative is 0.0205, right? Okay? Now, what does that mean? That means at 100 guitar string sets, the price is actually what? Decreasing about 2 cents. So remember, this is nothing new. What is derivative? Rate of change. How the price is changing. So after selling 100 guitar sets, the price is actually decreasing 2 cents. Per, so let me guys make sure you look per guitar set. Derivative is always something per something. Derivative is always something per something. The only thing I did new was that it's a derivative of a special case. It's the only thing new. Questions on that? Next word problem. An investment of $10,000 earns interest at an annual rate of 4% compounded continuously. Find the instantaneous rate of change, derivative, after 2 years. Okay? So you're starting with the formula. Your account equals 10,000 e to the 0.04 t. We're going to find the derivative, and then we're going to plug in 2 years. So let's do this together. Let's do this together. If you want to plug into the original, we can plug into the original. I mean, you can find the derivative first. Okay? So, how do I do this one? Well, here's what we do. Step 1. What happens to the 10,000? Stays in front. Then we have a little dilemma. I know the derivative of e to the x. Well, what's the derivative of e to the 0.04 t? Here's how we do that. Ready? So we're going to add that to our little special cases as well. Step 1, rewrite it. Step 1, rewrite it. Step 2, because it's not just a plain old t, we have to add one more step. If there's a number in front of the x or the t or whatever variable it is, step 1, rewrite it. Step 2, derivative of the exponent. What's the derivative of 0.04 t? What's the derivative of 0.04 t? 0.04. Stop there. And let's add that to our special cases. So in continuing with number 1, we'll call this 1b. If I had e to the 0.04 t, or x, let's choose x, to find the derivative, what's step 1? Rewrite it. And now, only if there's a number in front. If it's x squared or something like that, it's different. This is only if there's a number in front. You take the derivative of the number in front, it's 0.04. So, to make sure we understand this, if I had e to the 3x, step 1, rewrite it. Step 1, rewrite it, and what would I multiply by? If I had e to the 3x, I would rewrite e to the 3x times what? Times 3. What if it was e to the 4x? E to the 4x times 4. E to the 5x. E to the 5x times 5. It's always times the derivative of the exponent. So, to clean this up, 10,000 times 0.04 is 400. E to the 0.04 t. So I want you to plug 2 into the original, plug 2 into the derivative, and check it in the calculator. Plug 2 into the original, 2 into the derivative, and check it in the calculator. Put the original function in y1, put the derivative function in y2, check it in y3. Again, the nice thing about doing all this is you can check all of your work.
What I'm focusing on is what it all means. The calculator is just going to help us get the number. We need to know what it means.
So y1 is the original, 10,000 e to the 0.04x. y2 is the derivative, 400 e to the 0.04x. y3 is our derivative in the calculator. We're plugging in 2. What does 2 stand for again? 2 what? 2 years. And what will it tell me when I plug in 2 years? What does A stand for? A stands for, let's write it down. So T stands for time in years. A stands for how much money is in the account. So T is time in years. A is account. How much money is in your account? So you started with 10,000. What's happening 2 years later? You're starting with 10,000. What happens 2 years later? So for every word problem, we got to make sure we put down what is the input, what is the output, what is the input, what is the output. Okay, let's check our work, see how we're doing. So, y1 is the original, y2 is the derivative, y3 is checking the derivative. When I plug in 2 years, y1 tells me 10,833. So what does that mean? At 2 years, the account total is $10,833. So that just tells me total. 2 years have gone by. I now have 833 extra dollars. Now, y2 and y3 match at 433.31. So let's stop. 10 years later, I now have 10,833. Why are we doing derivatives? What's the point? What's the whole idea? Why do I have to figure this out? What is 433? 2 years have gone by. I now have this much money. What's going to happen to my account? It's going to go up or down. How do you know it's up? Positive. And how much is it going to go up by? $433.21. So this is telling me, yep. So at year 2, the account is increasing $433.31 per year. That's the rate of change at that time. That's the rate of change. That's how your account is changing. The whole point of everything we're doing, is how the account is changing. That's derivative. This derivative had an E in it, so we had to figure that out. We're okay? The only thing new is that it has an E. One more word problem, and we're done. One more word problem, we're done. I'm going to skip this next problem. I'm going to show it to you, but I'm going to skip it. I'm going to skip this next one, so I'm just going to show it to you real quick, but we're not going to do it. There's the one we just did. It's growing at a rate of $433 per year. The next part B I'm going to skip. It says, find the instantaneous rate of change of the amount in the account at the time that it has a balance of 20,000. I'm going to skip this one. But basically, you have your original, you have your derivative. They're trying to point out that when you take the derivative, you have 0.04 times the original. The original is the account. If you plug 20,000 in for the original, you get 20,000 times the 0.04, you get the answer of 800. Don't worry about this one. It's kind of a weird way to look at it. I like what we're doing. Okay? Last word problem. Here's what I want you to do. I want you to do this on your own. Number one, write it down. Number two, write down input, output. Input, output. Make sure you know that. Then you're going to take the derivative and estimate the number of locations at 2028. And 2028 is plugging in T of 48. Okay? So what you're going to do, read it, figure out input, output. You're going to plug in 48 into the original, find the derivative, plug 48 into the derivative, and explain. This one I want you to read on your own. I'm going to walk around if I need something. Big problem we have is we're not reading, making sure we understand all that stuff. It's a big part of this class. All word problems. It's not punching Y1, Y2, Y3. That's something that's getting easier. So much easier when I do it in copy, right? Read it, input, output, Y1, Y2, Y3. If Y2 and Y3 don't match, the derivative is wrong. This is the kind of stuff that happens on the exam, on your homework, on your quizzes. Read the word problem, input, output. See if you remember derivatives. People make it hard. Don't make this more complicated. One more minute. Make sure Y1 is the 1 and then Y2 and Y3 match.
All these things come up when you're on your own. You're like, oh, I can't copy anymore. What's going on? Not that bad. Making it harder than it is. Y1, Y2 and Y3 should match. If they don't match, something's wrong. And Y2 and Y3 should match. Let's get rid of any number.
All right, let's look at this. The problem says the model for the growth of a sandwich shop franchise is N of T equals negative 765 plus 42 L N of T, where N of T is the number of locations in year T, 0 is 1980, estimate the number of locations in 2028, which is 48. So T is 48. Now, here's the problem. We're trying to just calculate our way out of it. That doesn't work. You have to understand the problem. So first of all, what's the input? What's the input?
Locations.
No, what's the input?
Oh, 48.
What's the input in words? Time
Years.
in years. You're plugging in 48. 48 is 48 years. What's the output?
Locations.
Number of locations. If you don't know that, you're not able to do any word problems. Okay? Input, output is how it all begins. Good so far? Now, I need to find the derivative. Here's where most of you are making mistakes, which has nothing to do with today at all. You're forgetting what's the derivative of any number?
0.
0. The derivative of any number is 0. Then, what do you do when there's a number in front? Number in front stays in front. And then, the only new part of today is, what's the derivative of ln of t? 1 over t. So that becomes 482 over t. That's it. All of you are freaking out, thinking it's the hardest derivative ever. That's the derivative. 482 over t. 482 over t. Why? The derivative of a number is 0. The number in front stays in front. And the only thing you have to remember is the derivative of ln of t is 1 over t. If it was an x, it'd be 1 over x. Are we okay? Stop there. Do we have the original? Do we have the derivative? Now, what happened, because you're doing it on your own, number one, y2 and y3 wasn't matching because it was wrong. Number two, you can't write a sentence because you don't know the input and output. Those are the problems we have on the test and on the homework and the quizzes, is that we think we just plug in the calculator and it comes out. It's not how it works. Okay? So, in my calculator, I go to y equals, y1 is my original, negative 765 plus 42 ln of x. y2, which is my derivative, is 42 divided by x. And then y3 is the derivative in the calculator. We okay? So easy when we go over it, isn't it? You're like, oh. Okay?
So how do you get the y for y?
y1 is the original. y2 is the derivative.
How do you put it in the calculator? Because I was trying to
How do I do y3?
No, y1. Yeah.
Y1 and Y3.
How do I do y1 or y3?
The y1,
The Y1
y1
and
and y3.
Okay, y1 is this one. How do you type it in?
Yeah.
You type in negative 765 plus 482. ln is right here. Remember we practiced all the buttons? We practiced all the buttons? ln of x. We okay?
It's the y1,
It's
y3. It's bars.
Okay, so in y3, how do I type in y3? Let's do y3 now. y3 is math 8. X goes here. Here is y1. To do y1, it's vars to the right for y vars, number 1 for function, y1, and then x in the end. So vars to the right for y vars, bars to the right for y bars, 1 for function, 1 for y1. Okay, practice, practice, practice. Now we plug in 48. What's 48 again? 48 years. So 48 years have gone by. Now y1 is 1,100.9. y2 and y3 match. That means I did it correctly. So first of all, let's deal with this. When I plug 48 into the original, I get 1,100.9. What does that tell me? At 48 years, the total number of locations is 1,100.9. At 48 years, the total number of locations is 1,100.9. Are we okay? Then we get, I'm going to call it just 10. It's 10.04. Let's just call it 10. What is 10 telling me? I have been doing this business for 48 years. I look great for doing this business after 48 years, okay? I now have 1,100 stores. Will I have 1,100 stores forever? No. What's going to happen next year? How is my business growing? Next year, I'm going to have 10 more stores. How do you know it's more? Positive. And 10 is the number of locations. So this is telling me at the current rate, at 48 years, the number of locations is increasing 10 locations per what? Per year. That's what a derivative is. That's what we're spending our time on. Okay? All right. Stop. I'm going to take a 10